we're going to go over 3.5, limits at infinity. Yes, I am skipping over chapter 2 for one section only. This is still part of your limits exam. So our objective today, or our objectives, are determine limits as x approaches infinity or as x approaches negative infinity, and determine horizontal asymptotes. Okay? And in order to do this, we're going to be looking at end behavior again. So we did it today in class when we were looking at vertical asymptotes, and we're going to do it again when we are looking at the horizontal asymptotes. So let's take the case of f of x equals 3x squared over x squared plus 1. Okay? So when I graph it, it'll look something like this. So let me graph it. Let me do a quick sketch of it. I will have a horizontal asymptote at 3, and I will let you know how to, I'll show you how to find those horizontal asymptotes. And your graph looks something like this. So again, let me use that arrow notation once again to describe the end behavior of my function. So I see that as x approaches negative infinity, remember negative infinity is on this left side at negative x this side. So as x is approaching negative infinity, what is happening to my function? That line is getting closer and closer to my horizontal asymptote 3. So I'm going to say my function is getting closer to 3. Okay, and what is happening on the right-hand side as x approaches positive infinity? Well, I say as x approaches infinity, again, let's trace that line, trace the line, trace the line. As the x's are getting bigger, what is happening to the y's? Well, the y's are getting closer to 3. My function is getting closer to 3. And if I were to analyze this function numerically, and I put it in my calculator and use my table of values, I would see that if I have a function here, or if I have my table, it's negative infinity. I'm going to number this: negative 100, negative 10, negative 1, 0, 1, positive 10, positive 100, and positive infinity. Right? I see that at 0 it's going to be 0. At negative 1.5, 1 is going to be 1.5. At 1 is also going to be 1.5. At negative 10 is 2.97. At positive 10 is 2.97. At negative 100 is 2.997. And at positive 100 is 2.997. So at negative infinity it's approaching 3, and at positive infinity it's approaching 3. So I say in words, as x increases, or in this case over here on this left hand side, as x decreases without bound, f of x approaches 3. And on this other side, again, if I'm looking at it this way, so my x's are increasing without bound this time. So as x increases without bound, f of x approaches 3. Okay, so that leads me to my definition of horizontal asymptotes using limits. So here's my definition of a horizontal asymptote. Using limits. Okay, so now here's a definition of horizontal asymptotes using limits. So the line y equals L is a horizontal asymptote of a graph of f if the limit of f of x is equal to L as x approaches negative infinity, so negative infinity, or if the limit of f of x is equal to, as x approaches positive infinity, is equal to L. So again, that's a function something like that. It could look something like this. Okay, so it's approaching a certain number as x is approaching negative infinity to the left side, so maybe it's approaching 0. And then as it's approaching positive infinity from the right side, we will see that it also approaches that line L, which is y equals 0 in this case. Alright, so a function can, an important note right here, a function can have up to 2 horizontal asymptotes. So one from the left side and one from the right side. Okay? And also, functions that approach infinity have some of the similar properties that we've used before. So let me show you those properties again. So if I have the limit as x approaches infinity or negative infinity, doesn't matter, then the functions, if I'm adding 2 functions, then I can separate them and take the limit of each individually. So the limit of f of x as x approaches infinity or negative infinity, plus the limit of g of x as x approaches infinity or negative infinity, depending on what you started with. And again, so that's one of the properties. Another property is if I'm taking the limit of 2 functions and I'm multiplying them together, then I can separate them and take the limit of each of them separately, then multiply them together. Okay? So we have those 2 properties right here. Alright, so one property though that you need to know for sure is so I'm gonna write this. You have to know this, that the limit of a number over x raised to a power as x approaches infinity is equal to 0. Okay? And the same goes for when that limit of a number over x raised to a power as x approaches negative infinity is also equal to 0. So for example, if I had the limit of 3 over x squared as x approaches positive infinity, well, that's equal to 0. And if I had the limit of 7 over x to the, let's say, 5th power as x approaches negative infinity, that is also equal to 0. Okay, that's just something you need to know, because it'll help us solve limits that get a little bit more complex, like this one, for example. If I had the limit of 5 minus 2 over x squared as x approaches infinity, well, I know that I can separate it because it's 2 functions being subtracted, so I can separate that as to the difference of 2 limits. So the limit of 5 as x approaches infinity minus the limit of 2 over x squared as x approaches infinity. Well, this is the first one right here, is a property that I've shown you before. The limit of any constant, no matter what it's approaching, even if it's infinity, is just equal to that constant times. And then this one is the one that I just told you right here. The limit of a number over x raised to any power is 0. So we have 5 times 0, which is, oh no, not 5 times 0, 5 minus 0, I'm sorry, which is equal to 5. So that's my limit. That's what the limit is equal to. Okay, so now let's get a little bit more complicated. So let's see. If I had the limit of 2x minus 1 over x plus 1 as x approaches infinity, well, if I analyze this, I know that the numerator is just a line. So as x is increasing, my numbers on top are going to increase, so that'll approach infinity. And then the bottom, if I plug in 1, I'll get 2. If I plug in 10, I'll get 11. If I plug in 100, I'll get 101. So I see that if I keep increasing my x values, then the denominator is also going to increase. So that one also approaches infinity. Okay? So this gives me something that is equal to infinity over infinity. And this is called an indeterminate form. So that means I can't do anything with it. So I'm going to show you the long way to do this. Okay, here's the long way, and that you learned in pre-calc. The long way to do this is you find the limit as x approaches infinity. I'm going to divide my numerator by x, and I'm going to divide my denominator by x. So I'm going to get 2x over x minus 1 over x in my numerator, and in the denominator I'm going to get x over x plus 1 over x. Okay, and I'm going to separate that into 4 different limits because I can. So I'm going to do the limit of, as x approaches infinity, of, here's my numerator, that reduces of just 2, minus the limit of 1 over x as x approaches infinity, over, and then I'm going to take the limit of each of these in the denominator, so that is equal to 1. So I have the limit of 1 as x approaches infinity, plus the limit of 1 over x as x approaches infinity. Okay, so this is, again, this is a property that you already know. So when you have a limit of a constant, it's just equal to that constant, minus, I just showed you this other property right now. What is that equal to? 0. 0 over, again, a constant, limit of a constant, no matter what it's approaching, is equal to that constant, plus the limit of 1 over x is, again, just 0. So I have 2 over 1, which is 2. So my limit is equal to 2. Okay? So now I'm going to show you the shortcut. Okay? Here are some guidelines for rational functions, limit as at infinity. Okay, so if the degree of a numerator is less than the degree of the denominator, then the limit is 0. So if I had the limit of, say, x plus 1 over x squared minus 5 as x approaches infinity, look at the degrees of the highest, look at the highest degree. This is 1 and that's 2, so the bottom is bigger, so my limit is 0. Okay? Next one, if the degree of a numerator is equal to the degree of the denominator, then the limit is the ratio of the leading coefficient. So for example, if I had the limit as x approaches infinity of x squared plus 1 over x squared plus 5, then they're the same degrees. Oh, let's put some numbers in there. Let's say 3x squared plus 1 and 2x squared plus 5. Then the limit is just equal to the ratio of these leading coefficients, which is 3 over 2. That's it. And the last one is, if the degree of the numerator is more than the degree of the denominator, then the limit does not exist. So if I had the limit as x approaches infinity of 2x cubed minus 1 over 2x plus 1, look at the degrees. This one has a degree of 1, and this one has a degree of 3. So the limit does not exist.